Welcome to this explainer. Today, we are taking the nuts and bolts of chemical equations and turning them into a highly visual step-by-step workshop. We're not just looking at the big picture formulas here. We're going to roll up our sleeves and break down exactly how these molecular transformations actually happen under the hood. Picture a factory floor for a second. When we look at a completed airplane, we don't just see the finished product, right? We know there's a massively complex assembly line putting it together from thousands of individual parts. Well, chemistry is exactly the same. That overall balanced equation you usually see, that's just the finished airplane. To really grasp what's going on, we need to walk the factory floor and understand the underlying assembly line. And that brings us to this absolutely crucial definition, a reaction mechanism. This is the actual sequence of elementary steps that together comprise an entire chemical reaction. It perfectly captures our assembly line analogy. Reactants don't just magically teleport into products. No way. Instead, they steadily build, break, and transform, step by step, right at the molecular level. Here's our roadmap for today's explainer. 1. Organic reactions. 2. Redox basics. 3. Oxidation numbers. 4. Balancing redox. And finally, 5. Basic solutions. Let's kick things off with Section 1, Organic Reactions. Now, check out the stark contrast between these two primary organic pathways. Over on the left, we've got addition reactions. This is where an atom or molecule gets added to an unsaturated molecule, specifically one that has double or triple bonds. The reaction physically breaks that extra bond to make a single, fully saturated product. Fun fact, this is literally how the food industry turns liquid oils into solid margarine, just adding hydrogen atoms straight across carbon-carbon double bonds. Then, on the right, we have substitution reactions. Think of this like a molecular swap meet. One or more atoms replace another atom, or functional group, in a molecule. The overall framework of the molecule stays the exact same, but you swap out a specific piece. A great example from our sources is the creation of halothane, which is a powerful general anesthetic. It's formed by substituting a halogen atom for a hydrogen atom on an alkane. So simply put, addition builds up by breaking double bonds, substitution just swaps the existing pieces out. Moving right along to Section 2, Redox Basics. Stepping out of organic chemistry for a minute, we run into reactions driven entirely by the invisible transfer of electrons. So the absolute most crucial thing to remember whenever you hear the word redox, which is just short for oxidation reduction, is this classic mnemonic. It anchors exactly where those electrons are going. Leo says jur. Loss of electrons is oxidation, gain of electrons is reduction. In a redox reaction, electrons are literally handed off from one substance to another. The substance losing its electrons gets oxidized, and the one catching them gets reduced. They are intrinsically linked. You simply cannot have a loss in one place without a gain somewhere else. It's a total package deal. Which brings us to Section 3, Oxidation Numbers. Because electrons are, invisible, tracking their transfer can be kind of tricky. We need a reliable bookkeeping system, and that's exactly where assigning oxidation numbers comes in. Consider this table your ultimate cheat sheet for molecular accounting. An oxidation number is basically a positive or negative number assigned to an atom to show its degree of oxidation or reduction. Notice how free elements, think pure sodium metal or oxygen gas, stay completely neutral at an oxidation state of exactly 0. Meanwhile, inside compounds, hydrogen reliably acts as our +1 anchor, and oxygen is almost always our -2 anchor. And here's the golden rule. In any compound or polyatomic ion, the sum of all these individual oxidation states has to exactly equal the total overall charge of the molecule. If an atom's oxidation number goes up during a reaction, well, it lost negatively charged electrons, meaning it was oxidized. If the number goes down, it gained electrons, so it was reduced. All right, let's roll up our sleeves for Section 4, Balancing Redox. Now with redox, just balancing the physical atoms isn't going to cut it. You have to balance the electrical charge too. What you're seeing here is our syllabus for the half reaction method. It breaks a seemingly impossible equation down into a really systematic checklist. The whole trick is to divide the overall reaction into two separate halves, the oxidation part and the reduction part. By treating them separately, we can methodically balance both the mass and the charge before snapping the whole puzzle back together. Let's chunk the first half of this procedure into what we'll call the setup phase. Here, we're focusing entirely on making sure our physical atoms are perfectly balanced on both sides. First up, you separate your half reactions. Second, balance any main elements that aren't oxygen or hydrogen.
Third, and pay attention because this is a very strict rule for acidic solutions, you balance your oxygen atoms by adding water molecules to whichever side needs them. Finally, step 4, you balance those hydrogen atoms you just introduced by adding protons, or H+ ions, to the opposite side. Okay, so at this point, your atoms are perfectly mirrored, but your electrical charges are probably totally out of whack.
So with the mass balanced, we enter the Polish phase. This is where we finally use electrons to balance the charge. Step 1 is to look at the total charge on both sides of your half reaction and add negatively charged electrons to the more positive side until the charges match perfectly. Step 2 is absolutely crucial. The number of electrons lost in the oxidation half must perfectly equal the number gained in the reduction half. You'll often have to multiply one or both entire equations by a coefficient just to make those electron numbers match. Finally, step 3, you triumphantly recombine the two halves back into one clean equation, canceling out the electrons and any of those duplicate waters or protons that pop up on opposite sides. And lastly, section 5, basic solutions. Okay, so the previous steps cover acidic solutions where protons are just freely floating around. But what happens if our reaction is in a basic solution? One full of hydroxide. Well, the easiest way to handle basic solutions is this brilliant trick called the fake acid method. You literally do the exact same steps we just covered, basically pretending the solution is acidic to get your balanced equation. But then you execute a final pivot. For every H+ ion currently sitting in your equation, you add a hydroxide ion, an OH-, to both sides of the reaction. On the side where the H+ and OH- meet, they instantly combine to form liquid water. Finally, you just cancel out any duplicate water molecules on either side of the arrow. It's a highly elegant shortcut that totally saves you from having to memorize a whole separate set of rules. The exact same mechanisms we just walked through, addition, substitution, and those tiny invisible electron swaps, these are literally the fundamental drivers of the physical universe. Think about it. If a simple redox reaction can rust an entire iron ship or power the battery in the device you're using right now, just imagine the millions of unseen chemical mechanisms sparking inside your own cells at this very second to keep you alive. Pretty mind-blowing, right? I encourage you to take these step-by-step frameworks and keep exploring the incredible chemistry happening all around you. Until next time, keep questioning and keep learning.